Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, good afternoon everyone. Now before we begin with today's lecture, just a quick announcement. Your question sheet for assignment 2 is now available on Waddle with the associated data sets. Okay, and the link for uploading the assignment is also live. The process is exactly the same as it was for assignment 1, right? So there are a couple of data sets, a series of questions, you need to answer them, write up a report which consists of selected R codes and outputs that you put into the report, the main body of the report, and you upload the file as a single file onto Waddle. Okay, make sure the assignment is typed up. Okay, and it's not scanned version of like a handwritten note or a printed copy. Okay. If it's not typed up, we will not mark the assessment and you get a 0 out of the mark, 0 for the mark, okay? For the first assignment, I disregarded that, right? So I think there were only just a few assignments which were not typed up. But this time around, we're going to be very strict about that, okay? Secondly, just like for your first assignment, the R codes, all the extra R codes that are not in the main body of the report, make sure you put in as an appendix at the end of the actual report itself, okay? And you can upload then your Word document or your PDF document onto the upload link. Are there any questions? No? Okay. With regards to the content, the second assignment is mostly based on multiple linear regression. Okay. And most of the content that covers the topics for your second assignment will be completed by the end of this week. Okay. So once we finish this week's lectures, you should be able to attempt the assignment completely. The due date is 21st of May, so which is essentially 2 weeks from today. So Tuesday at 9 a.m. So make sure you submit your assignment before 9 a.m. on Tuesday, 21st of May. Okay, let's continue from where we left off last week. So last week we were looking at running multiple linear regression with a categorical variable. In particular, we were focusing on a categorical variable which had multiple categories, not just 2, but more than 2 categories, right? Just a quick recap of what we did last week. So we were looking at house prices in a particular district and taking into account various different factors or various different predictors in terms of modeling the house price, right? We were modeling log price based on a factor variable called condition, which denoted the condition of the house, and it took on 5 values, 1 through 5, as you can see in that box plot. Okay, and we expect that there are differences in the prices of a house based on what condition they are in, based on what the house condition is, right? Visually, we can sort of see that in the box plot, but as you know, box plot is not really a statistical test, right? And last week we had looked at ways of testing that out, right? And we saw that multiple regression offers a very good way of testing the underlying hypothesis that all the group means are equal, right? So the mean house price for each of the 5 conditions are equal. That kind of hypothesis test can be performed under the guise of a multiple regression model, right? So what we did was we fitted a model. In this case, we also had log square foot living as an extra predictor, right? Over here, we can think of log square foot living as what we call a control variable. Okay, it is a predictor, but we're not really interested in how house prices relate to log square foot living, but we still want to control for that, right? So we want to look at the effects between the different house conditions and the prices because of those different house conditions by controlling for the living area. Okay, so essentially, again, we talked about this last week, but just doing a quick recap. Essentially, what we're saying is that we understand that house prices will be different because of different living areas, living sizes. Okay, so controlling for that area of a house, we want to see whether the condition still has any impact on the price differential. Okay, and what we talked about last week was that these betas that we estimate for the various different condition values, so house condition values, are essentially an estimate for the difference in the group means. Okay, so for example, when you have a house, all houses of condition 2 and all houses of condition 1, their difference in mean, so mu2 hat minus mu1 hat, okay, is estimated by our beta for condition 2. So beta 2 hat gives us the estimate for the difference in the group means. Okay. Remember those beta 2 hats, beta 3 hats, so on are just these estimates that we have estimated from the multiple linear regression model. Okay, right. So again, we talked all about that last week, and we saw that essentially the tests under a multiple linear regression model, right? So the overall F test that you can do is just one way of testing the hypothesis that beta 2 equals beta 3 equals beta 4 equals beta 5, which equals 0. Right? So all the betas associated with those house condition values are all equal to 0, versus the alternative that some of the beta i's are non-zero. Okay, doesn't mean that all of them have to be non-zero, right? We can still have some values which are non-zero, and we can have others which are approximately equal to 0, right? And that's where we had essentially ended our lecture, right? As we can see here, if we look at the associated t-test for those 4 parameters, for those 4 estimates, we notice that only one produces a significant difference between the group means, right? The other 3 are not significant, right? So beta 2, beta 3, beta 4, their estimates are not significant, meaning that these 3 differences in particular are not significantly different from 0. Okay, only the last one is in fact significantly different. Right? We'd also seen that when you're doing multiple comparisons, you need to adjust your significance level accordingly, right? So in this case, since we are performing 5 tests, right? 4 tests, we need to adjust the alpha value according to that, right? So applying the Bonferroni adjustments, okay, instead of using alpha equals 5%, right, we would use a new alpha level, call it alpha star, which would be alpha over 4, based on the number of tests you're doing. Okay, right, but even based on that, we would see that those values still remain significant. Okay, that last value still remains significantly different. Now, what we want to talk about today is, firstly, understand that this particular representation of the multiple linear regression model is only checking for 4 comparisons, each which has mu1, as you will see here, as the reference level, right? Your condition equals 1 was the reference level, right? What about the other comparisons, right? What about, for example, is there a significant difference between house prices when condition is 5 versus when condition is 2, right? So as we can see in the box plot, so if you want to compare the house prices for condition equals 5 versus condition equals 2, we sort of expect that their differences are also, the difference in the means looks quite different from each other, right? The difference between 1 and 2, as we can see, is not that different, right? Similarly, difference between 3 and 4 doesn't seem that different. For that matter, difference between 3 and 5 doesn't seem to be that different, okay? But we want to numerically and numerically test for these differences, right? So perform tests which can tell us conclusively whether the group means are different between the various different groups, okay? And as I said last week, we can do so by essentially changing the reference level in our factor variable, right? So in our condition variable, if instead of making our reference level as 1, condition 1, we can set it to be equal to condition 2 or 3 or 4 or 5, whichever we want, okay? And then perform the test, right? So for example, if I were to set the condition to be equal to 2, right, then all my betas in my regression model would therefore estimate these quantities, right? So mu1 hat minus mu2 hat. The next one would be mu3 hat minus mu2 hat, and then mu4 hat minus mu2 hat, and mu5 hat minus mu2 hat. Okay, this is where condition 2 is my reference level. Okay, I'll just get to in a second how we actually can do that in R, but assuming you can do that, those are your estimates, right? So this is your new beta 2 hat, and beta 3 hat, beta 4 hat, and so on. Okay, right? So how we can do that in R? As I said, I'd introduced this function last week, but didn't give details. The function you use is called relevel. Okay, so relevel takes in as input a factor variable, right? So factor of condition is the input that we provide, and as an extra argument, you tell relevel which new level is going to be your reference level, right? The command for that simple, it's just reference equal to the name of that level. Okay, you'll notice we give the number 2 within quotes, right? Because remember, for a factor variable, the numbers do not stand for numbers. They are just codes for different categories, right? So the numbers 1 through 5 are not the numbers 1 through 5, but they are codes 1 through 5 for the 5 conditions of the house. Okay, so that's why we provide it within quotes. Okay, it is entirely possible that your categorical variable do not have numbers as codes, but maybe letters of the alphabet or full names themselves, right? So for example, you can have a variable in a different data set, say called gender. Okay, it's a factor variable, right? There are 2 ways that you can code gender. You can use the numbers 0 and 1, say to represent males and females, okay? Or in fact, you can code gender using these letters as codes themselves. Okay, does everybody get that? Right? So that's why these numbers 0 and 1 are also treated as just codes, okay? And that's why it's necessary that you provide those values within quotes, okay? If you just say reference equal to without the quotes, the function will give you an error. Okay, right? Once we've re-leveled our factor variable, we can fit the model again and look at the summary of the model, look at the coefficients, okay, and we'll see that those coefficients are going to give us those same estimates as we've calculated here, right? The group mean differences. So notice how the difference between mu hat 3 and mu hat 2 is 0.1620, right? Let's see whether that is in fact what we get in our model summary, right? So you'll see again the third line, which is the value of the estimate for factor condition 3 is 0.1620, exactly as we had calculated previously. Okay? Is everybody clear on that? Right? So re-leveling just makes a new level, a new category, your reference category, okay? But other than that, those estimates are still measuring the same thing, right? The estimates will always measure the differences in the group means, okay? Which group means are they measuring the difference between? The actual level itself and the reference level that you've chosen. Okay, right? Now, for this variable that we have, factor condition, we have got 5 different levels within condition, right? 5 different categories within condition, right? So for such a variable, there are in fact 10 possible pairs that you can test for differences, right? 10 unique pairs, right? There are 5 options or 5 categories to choose from. A pair has 2 categories, so there are 5 choose 2 or 5 C2, however you want to write it. That many options available of possible pairs. Okay, so 5 choose 2, which again you can tell R to give you that result, is 10 unique pairs. Okay, so if you want to perform a complete test of differences in group means, you actually need to evaluate 10 different tests, okay, 10 different comparisons, right? Which we can again do using that re-level function, okay, each time making a new category our reference category, right? So we've already done it for reference level 1, we can do it for reference level 2, we can do it for reference level 3, reference level 4, and so on, right? But again, keep in mind, when performing these tests at the overall significance level of 5%, we need to adjust the individual significance level so that it takes into account the fact that we are doing multiple tests, right? So given that we are doing 10 tests, okay, 10 comparisons, the test significance level is no longer 5% for each individual test, but it is 5% divided by 10, or 0.5%. Okay, so each test is now much more stricter in terms of its significance level, or in terms of what is the allowed type 1 error. Okay, so the allowed type 1 error now for each individual test is only 0.5% rather than 5%. Okay. So in these commands, again, very quickly, all we are doing is re-leveling the re-leveling the factor variable condition with the new reference category, okay, and then fitting the model, right? Now, given that we are doing it again and again, we are saving these models as different models, right? So the first model, mod.1, is with reference category 1, okay? The second model, mod.2, is when reference category is 2. Okay, we do that so on all the way up till reference category 4. Okay, obviously we don't re-level it when reference category is 5. Okay, given that we still have the 5th category, but we don't need to do that last re-leveling. Can anyone tell me why we don't need to worry about that 5th option? Remember, we're just doing bivariate comparisons, right? We're doing pairwise comparison, right? If you test, for example, mu5 versus mu1, which is done in this first re-leveling, okay, then you don't need to make reference category 5 because that test is already performed. Okay, right? So it's just the inverse which we don't really have to model for separately. Okay, those tests are already included, right? Then once we've got these 4 different models, okay, all we then need to do is extract out from each of these models the beta hats, okay, and their standard errors for the beta hats. Okay, by extracting out this information, we can perform the required test. Right, the test being mu A is equal to mu B versus mu A is not equal to mu B. Okay, A and B are just generic values, right? They'll stand for 1 through to 5, the condition values. Okay, right? And remember, in order to perform these tests, we're choosing alpha level, our type 1 error, not as 5%, but 5% divided by 10, so 0.5%. Okay? A quicker way of performing this test is to produce a confidence interval rather than evaluating the p-values. Okay? So the confidence interval for a model can easily be evaluated using the confint function. Okay, the confint function takes as input a particular model, okay, and output is the CIs for betas and all the betas in the model, right? It produces confidence interval for all the betas, the estimated coefficients in the model, okay? All you need to do is provide as input along with the model, the alpha level, right, the significance level. In this case, when we're using confint, we provide alpha as 0.005 or 0.5%. Okay, so for example, for our first model, mod.1, remember mod.1 is when reference level is 1. Okay, we provide the level. Again, remember the alpha level, the significance level is based on 0.005, 0.5%, okay, giving us the required confidence intervals. Okay. Now, in order to do the actual pairwise comparisons where we are comparing the group means, okay, we don't need the intercepts. We don't need the confidence interval for intercept as well as for our log square foot living area. Okay. So if you just want some of the estimates or confidence interval for some of the estimates and not all, okay, you can just provide tell R which estimates or which confidence interval to produce. Right? That can be easily done. Since we don't want the first and the second, just want the third, fourth, fifth, and sixth. Okay, we provide that as an index or as the values that we want. Right? Remember, confidence interval, the output from that confidence interval, okay, is just the series of confidence interval. Right? We don't want the first and the second, but everything after that. Right? We want all these values at the very end, so we'll store them in another object. Okay, you can store it wherever you like, right? But notice it gives us the appropriate, given that our alpha level is 0.5%, right? We essentially have a 99.5% confidence interval, right? As you can see over here, the central area is 99.5%. Between 0.25% and 99.75%. Okay, right? So all these tests, or all these confidence intervals are produced at a new alpha level, call it alpha star, okay, which is 0.005. Okay. Now remember how you can use confidence interval to perform hypothesis test. If a confidence interval includes the value of 0, that means there is not enough evidence to reject your null hypothesis. right? So you must assume that the null is true, or you don't have evidence to reject the null. And you'll notice that the first three, all of them include the 0 value in the interval. Okay? So all those three tests suggest that those group means are not different from each other. The only group mean that is different from each other is mu5 versus mu1. Okay? Right? What about all the other conditions? So now we'll set reference level as 2. Okay? We can again produce the confidence interval. The reference level 2 is saved in model 2, so mod.2. So we produce the confidence interval for mod.2. Again, we can suppress the values for intercept, log square foot living, as well as for factor condition 1. Right? Now, we don't need factor condition 1 because that test is already performed, although in the opposite direction, in the previous setup. Right? So we've already compared mu2 versus mu1. Mu1 versus mu2 is going to be exactly the same. Okay, just the signs or the order is reversed. Okay, so again, we can suppress the first 3 rows and only produce the last 3 rows, right? So the command for that would be saying only produce rows 4 through 6. Okay, again, I'll save these intervals in int.2. Right, again, notice all we have to do to perform our test is to see whether those intervals include the value 0. Right? In this case, none of the 3 intervals include the value of 0, meaning all these 3 confidence intervals provide strong evidence to reject the corresponding null hypothesis, which means that, for example, for factor condition 3, mu2 is not equal to mu3. For the next one, mu2 is not equal to mu4, and the last one as well, mu2 is not equal to mu5. Right? All these 3 pair of means, are different from each other. Okay, significantly different from each other. Next, we do it for reference level 3, again producing the confidence interval, and we can perform the same test, again, just to check whether those values of 0 are included in the interval. If not, then we have strong evidence to reject the null. Again, in this case, we do. So we say that mu3 is not equal to mu4, and mu3 is not equal to mu5. Okay. And then the last one, which is when the reference level is 4, and the last comparison is 4 versus 5. So mu4 not equal to mu5. Okay, again, this also still provides us strong evidence to reject that null hypothesis. Okay, does everybody get that? Right? Now we can combine all of these 10 intervals that we've produced, okay, together into a single object. Right? Again, this is just a little bit of our code helping for you. Right, so all the intervals are now stored in a new object called pw.comps. You can give it any name you want. Okay, the reason why I named it this way is basically pairwise comparisons. Right, just that. And what I'm now doing is combining those intervals from model 1, model 2, model 3, model 4. Okay, which I've stored in objects int.1, int.2, int.3, and int.4. Combining them together. Okay. Now these are row combinations, right? So I'm combining or adding new rows to the previously existing rows, right? So that's why you use the command rbind. Rbind is for combining rows of data. Okay. Similarly, if you want to combine columns of data, you use the command cbind. Right, cbind is a useful command when you're combining different vectors into a single object, a single database, right? So in this case, I combine all the pairwise comparisons from my 4 models, okay, label them, right? And then when I produce the single object, I can see all the 10 pairwise comparisons. Okay, and taken together, I can see that there are only 3 intervals which which produce not or non-significant results. The other 7 produce statistically significant results. Okay? Does everybody get that? Right? So in my actual complete pairwise comparisons, when I compare all group means with all the other group means, okay, there are only 3 which I don't have evidence to say that they are not equal to each other. For all the others, I have strong evidence to say that the means are not equal. Okay, right? And that sort of completes the whole picture of comparing group means. Okay, right? Any questions? Yep. Yeah, so the question was, is there another package or a function which can do these pairwise comparisons? Yes, there are, right? If you're interested, really interested, just do a Google search of doing pairwise comparisons using ANOVA or using R in ANOVA. Sorry, using ANOVA in R, and you will see various different packages. There are just quite a lot of functions, and that's why I'm not mentioning them here. The other reason I'm not mentioning them here is doing pairwise comparisons is not the sole purpose of why we're doing multiple regression, right? It's just one of the byproducts that we have of you having the regression techniques when doing group comparisons, right? Although this is a cumbersome way of doing it, but it actually shows you the mechanics behind it, what you really are doing, right? Okay, and that's why we stick with this method. There are, as I said, many other functions which can automatically do that, okay? The problem with me telling you such a function is that you then don't pay attention to the ideas and the constructs behind it, right? Or there's a possibility that you will not worry too much about the construct, okay? Over here, we want to really focus on the underlying theory, okay? Right? But yeah, do a quick Google search and you can easily find it, okay? Now let's take this model a little further, okay? So we are now moving away from pairwise comparisons, right? Again, remember when we talked about pairwise, or when we started talking about pairwise comparisons last week, we were talking in terms of the context of multiple linear regression, right? So we are still trying to fit a predictive model where we can predict the log price based on the various different predictors, right? Whether it's square foot living area, whether it's the number of bedrooms, bathrooms, condition of the house, so on and so forth, whether there is a waterfront or not, right? So still the idea is we want to be able to explain the variation in log price, right? So coming back to that problem, okay, and moving away from just doing simple group comparisons, right, where we are not really tapping into the full potential of a regression model, we come back to this scenario of predicting behavior of price, okay? And in that regard, or in that context, just having the factor on its own, as we've seen before, all it does is it allows us to have multiple linear models with different intercepts to explain the log price, okay? But what if we believe that not just the intercepts are different, but the slopes are different as well for the different categories, okay? We saw the same issue in waterfront case as well, right? And we can do so in a categorical variable with more than 2 categories, right? So essentially, we add the interaction term, right? And remember, the interaction term, all it does is now allows us to have not just different intercepts, as well as different slopes. Okay? The way it allows us to model different slopes is now we believe that the effect of log square foot living area on the log price is not constant, but it depends on what condition the house is in, right? Okay, and that's what this interaction allows us to model. Okay, so when we produce, or when we fit that model and look at the summary statistics, So these are just the coefficients and their standard errors and their p-values. Okay, we'll notice now, apart from the slopes or the coefficients for the different categories, we also have now different estimates for the 4 interaction term. Okay, so the first 4 are for the different categories, meaning providing us with different intercepts. The last 4 estimates, coefficients, are for the varying slopes. Right? So log square foot living with the factor condition of 3, okay, produces a different effect on log price, okay, and so on and so forth. Right? You'll see some of these are negative, okay, right, and some of them, in fact, just one of them is positive, right? How do you interpret this? What do we mean by a negative intercept here? Sorry, a negative estimate here? We're basically saying that when condition of the house is 3, okay, then the effect of log square foot living area on the price, okay, which is measured by this parameter, this estimate, is reduced by this amount when the condition of the house is 3. Okay, with reference category. In this case, you'll notice that the model reference category is 4. Right? It's the last reference category that we had used for condition, so that's where it is stuck at. So in reference to when the house condition is 4, if the house condition is 3, then for the same square foot living area, okay, the effect of log square foot living area is reduced by that proportion, that portion. Right? So the slope is no longer 0.8351665, but it is 8351665 minus 0.013. Yep. Is it reduced by, sorry, what? No, so the idea is that for every square foot living area, right? So without the interaction term, right? So every square foot of living area tends or is related to a 0.83 increase in the log price, right? Okay, all that part is obvious to everyone, right? So in that model, if the condition of the, forget the condition of the house and so on, for a given square foot living area of a house, if the square foot living area of the house increases by 1 square unit, or 1 unit, okay, then the log price of that house will increase by that amount, okay, right? Having an interaction term or having a condition, a factor term, means that now we're basically saying if the condition of the house is 3, okay, right, and not the reference condition house, which is 4. So compared to condition house 4, if the condition of the house is at 3, okay, then the base price, okay, the intercept would increase by that much. Right? The intercept is set at 6.75, but now, given that the condition of the house is 3 and not 4, the new starting price or the new intercept price is that much higher. Okay? But now when we add the interaction term as well, okay, then what we are saying is with the interaction term, the rate at which the price is increasing, which is that amount, 0.835, for every increase in the log square foot living area, okay, because now the condition is 3 and we've modeled for that, okay, it now increases by a slightly lower amount. Okay, it may be easier to see it this way, so let me quickly add a page. Right. So let's look at the two comparison models. Okay, so one situation, we have condition is equal to 4. Okay, if the house condition is equal to 4, we're basically saying, based on our model, that log price would be equal to beta 0 plus beta 1 log living area. Okay. Plus nothing else after that, right? Because all the other intercepts, all the other coefficients or estimates would be 0 because we're looking at the reference condition house, right? So none of these will have any impact on the log price, okay? So we have that when the condition is 4. But now when the condition is 3, log price. Okay, by the way, these are all estimated values, right? So it should technically have hats on top of them. Okay, what we have is beta 0 hat plus beta 1 hat for log living area, plus all the estimates when the condition is equal to 3. Okay, which relates to beta 2 here. Okay, and beta 6 here, right? So we have plus beta 2 hat plus beta 6 hat times log living area. Okay, so when the condition is 3 and not the reference condition 4, our model, our predicted log price, is given by this new intercept, which is beta 0 hat plus beta 2 hat, and a new slope as well, which is beta 1 hat plus beta 6 hat. Okay? Does everybody get that? Right? And that's what having a categorical variable and an interaction with that categorical variable does to our linear or multiple linear model. Right? For the reference category for condition, the log price depends on the log living area based on this model. Right? It has a particular slope, it has a particular intercept, beta 0 hat, and it has a particular slope, beta 1 hat. Okay? But now, if we look at a house which has condition 3 and not 4, okay, and then its intercept is now different, okay, and it's equal to beta 0 hat plus beta 2 hat. And its slope is different as well, which is based on beta 1 hat plus beta 6 hat. Okay, right? Now, based on the numbers that we've got, beta 0 hat plus beta 2 hat, given that both of these are in fact positive, right? So beta 0 hat, let me just get rid of all that. So beta 0 hat and beta 2 hat, both of them are positive, okay? My new intercept is higher than beta 0 hat. Okay? So if a house has condition 3, okay, it starts at a higher level. Right? So the straight line model which has a higher intercept. Okay? And not only that, beta 1 hat compared to beta 6 hat is negative, which means that this new slope, beta 1 hat plus beta 6 hat, is in fact lower than my reference slope, right? The reference category slope. Okay? Which means that if the house condition is 3, then the increase in price, the increase in log price, is no longer equal to beta 1 hat for every unit increase in area, but slightly lower than that, reduced by the amount beta 6 hat. Okay? Does everybody get that? right? In fact, if we were to plot all of these five different models, so one for each condition of the house, you'll notice the difference in the slopes, right? So when the condition of the house is 5, you get the red curve, right? So this, notice, has the lowest intercept to begin with, okay, but has the highest slope, okay, right? And then when you take into account all the other conditions, C1 through to C5, they all produce different sloped lines with different intercepts. Okay. In particular, if you look at C3 and C4, the one that we just were talking about, which is sort of the maroon and the green curve, okay, you'll notice that the green curve has a slightly higher slope as compared to the maroon curve, which has a slightly lower slope, which we just sort of saw in our numerical evaluation, right? The slope for just condition 4 is slightly higher than the slope for condition 3. Okay? And so we can visually sort of confirm that. Okay? Does everybody get that? Right? So your interaction produces your different slope scenario. Okay. Now the next bit is, once you fit the interaction term, the first thing you always want to check for is whether the interaction as a whole is significant or not, right? If it is not significant, statistically significant, then you don't really need the interaction term, right? In sort of practical terms, the test of significance is essentially testing whether all the slopes for the 5 different conditions is identical, or do you need a model with different slopes, right? So you're testing a model with same slopes but parallel lines, okay, or different slopes and therefore non-parallel lines, okay, right? So you can produce the ANOVA for the model that we've just fit and look at the line representing the interaction, okay? And just like for the factor variable, the interaction with the factor variable is always included in a single line in the ANOVA results, right? So you don't have each category represented differently, right? Which is good for us, convenient for us in testing the overall significance of the interaction, right? So you look at its F statistic, okay, and corresponding p-value to carry out the test whether each of those betas, so in this case the null hypothesis is beta 6, beta 7, beta 8, and beta 9 are all equal to 0, versus the alternative that at least some of these are non-zero, right? So some of the beta i's are non-zero. Okay, right? But again, keep in mind the order of your variables does matter, right? So in order to test the significance of the interaction, you must have interaction fitted as the last term. Okay? Right? Does everybody follow that? Okay. If you don't want to worry about the order, then you fit 2 models. The smaller model, which does not include the interaction term, and the larger model, which does include the interaction term. Okay, then it doesn't really matter in which order you fit the model. Okay, then all you do is compare the smaller to the larger model using the ANOVA function. Okay, does everybody get that? Right, and that still does exactly the same test. Any questions? No? Okay. Just a quick note on interactions. Okay. One problem with including the interaction term, and particularly if the interaction term is significant, is that we then lose the simple relationship that we had between the group means, or the difference in group means, and our estimated coefficients, right? Remember, in the model without the interaction, okay, the estimate for each value of the condition represented the group mean difference, right? So, for example, the estimate for factor condition 2 represented the group mean difference between condition 2 and whatever the reference condition was, right? This now no longer is true if we have an interaction term, okay? If you have an interaction term, then the difference, so that difference between, say, mu2 and mu1, over here we're assuming 1 is your reference level, okay, is no longer just beta 2, as it would have been in the previous setting, okay? Now it looks like this big setup that we have at the bottom. Because now when reference condition of the house is 2, okay, we don't just have beta 2, which is playing a part in our model, but we also have its interaction term also playing a part in our model. Right? Does everybody get that? Okay, and so you'll notice that that group mean difference, mu2 minus mu1, is not just dependent on beta 2, but dependent on beta 0, beta 1, and beta 2, and beta 6, the coefficient for the interaction term. Okay? Does everybody get that? Right? But then again, it's not that much of a problem, because if we really just want to compare group means against each other for statistically significant difference, we would always fit a model without interaction. Okay? Any questions? No? Okay. Now, before we look at the overall sort of model diagnostics, which will help us, first of all, understand whether all the assumptions that we made for our model fitting have been met and so on, right? We'll spend rest of today talking about interpretation, okay? In particular, interpretation of your regression equation, what it means and what it does not mean and so on, right? We've already touched upon a lot of the interpretational information when we were fitting all these individual models, okay? But we'll look at one final sort of overview of interpretation before we move on to the diagnostics, okay? You have to be careful about interpretation of the model, particularly how you interpret the coefficients in a multiple linear regression setting, okay? As compared to the simple linear regression, the interpretation is a lot more involved, a lot more complicated, okay? As you'll see in this simple example, right? So when we were fitting, say, for example, simple linear regression, where you just had one predictor, for, in this case, for instance, bedrooms, which was being used to predict a log price, right? Interpretation of the coefficients was very simple, right? For example, the interpretation of the intercept, which has a value of 12.39, okay, means that that's our intercept for the model, right? So structurally speaking, when the number of bedrooms is 0, okay, log price would equal 12.39, okay? It has no practical meaning, right? Because when a bedroom is 0, you typically will not have a house, an actual house, which has 0 bedrooms, okay? So practically speaking, functionally speaking, it has no meaning at all, okay? But in a structural sense, in a mathematical sense, okay, an intercept just provides a way of anchoring the model, okay? More importantly, bedroom, its coefficient, which is in this case 0.19, okay, has the interpretation that whenever you increase the bedroom by 1 unit, meaning if you just increase 1 bedroom in a house, okay, then we expect the log price of that house to increase by the amount 0.19. Okay, right? Which means that the price of the house would increase by the amount e to the 0.1945. Right? Okay? Now remember how exponential functions work. E to the positive 0.1945, okay, is going to give you a number which is greater than 1. Right? So in effect, it's basically saying that the price will increase if you increase the bedroom by 1 unit. Okay? Right? And that was pretty simple in a simple linear regression setting. But as we go into the multiple regression setting, right? So now we have not just bedrooms, but have the log square foot living area, bathrooms, and so on in our model. Okay? Notice how all of the variables are quantitative, right? None of them are categorical, okay? Now the interpretation becomes a little more tricky, right? Firstly, when you're looking at, for example, again, the intercept, the estimate for bedrooms, in this case it is negative 0.0735, okay, it's 0.07, negative 0.07. When you're trying to interpret this value, given that you're working in a multiple regression setting, okay, you have to keep in mind that it still sort of represents the change in log price when you increase the number of bedrooms in a house by 1 unit, okay, but is based on the condition that you hold everything else constant, meaning you hold everything else fixed. They are not allowed to change. Okay, so you're basically looking at a house which has the same log square foot living area, the same number of bathrooms, but you're just increasing the bedroom by 1. Okay, in that scenario, the log price decreases by this amount, negative 0.0735. Okay, or the price itself will change by amount e to the negative 0.07355. Sorry. Okay. Right. In fact, this number e to the negative 0.0735 is going to be less than 1. All right. So in this case, what we're basically saying, if you increase the bedroom number of bedrooms in a house by 1, the price will decrease compared to one which has 1 less bedroom. Okay? That is under the condition that everything else is held constant, meaning you can't change the log square foot living area, you can't change the number of bathrooms. Okay? All right? Now, in a lot of the scenarios, practically speaking, that may not always be possible, right? Okay, it is reasonable sort of to expect that if you just increase the number of bedrooms in a house, okay, then generally speaking, the area of the house will increase along with it, right? Okay, bedrooms are typically of a standard size. At least there is a minimum size. You can't really have a very small bedroom, right? So if you're going to add these numbers, okay, then generally speaking, you're going to increase the log square foot living area. Okay, same goes with, say, increasing the bathrooms and so on. Okay, right? So in practical sense, holding other variables as constants may not be always feasible or possible. Okay, or meaningful to explain, right? But we are talking more in a statistical or in a model sense, right? So we basically, in a sense, you're comparing two different houses where roughly the same living area and bathrooms apply, but the bedrooms are different between each other. Okay, and in that scenario, the price of the house which has the higher number of bedrooms is expected to be lower. Okay, and that's what this model states. Okay, whether it's in fact true or not in reality, we don't know, but the model suggests that. Okay. So, and the reason why it becomes tricky, right, holding things constant, okay, is because, as I said, these three variables in particular that we are looking at, they are inherently related to each other. Okay, bedrooms, square foot living area, and bathrooms are going to change in a sort of a known manner, right? Meaning, if you increase one, then more often than not, you expect the others' values to increase along with it. Okay, that can sort of be confirmed by looking at the correlations between these three variables. Right, so you notice the correlation between bedrooms or the number of bathrooms, just given here, or the bedrooms and the square foot living area. They all have positive correlation. Okay, right? So it is not practically reasonable to expect to hold something constant and just increase the other variable by a certain number of amount or certain value. Okay, they go hand in hand, right? But for interpretational purposes, okay, you can sort of look at this model parameters, these estimates, and interpret their values or interpret their effects on log price, okay, under these sort of unreal conditions. Okay, right? In this case, for instance, correlation is not that bad. Okay, they're not high correlations. Okay, but when the correlations between the predictors becomes really high, okay, the interpretation and in fact the model fitting itself becomes quite tricky. Okay, we will come back to this problem of correlations between the predictors at a later stage once we've already looked at diagnostics. Okay, so once we've considered diagnostics, we'll come back to this scenario. By the way, this is called multicollinearity. So the problem of multicollinearity, right? So multicollinearity refers to your predictors being correlated with each other, okay? And how we can tackle that, okay? One of the common, not always, okay? Keep in mind that this will not always happen, but one of the common results of you fitting a model with multicollinearity variables or correlated variables is that the estimates of the coefficients change their signs. Okay, so notice in the simple linear regression model, when bedroom was fitted, it had a positive coefficient, right? Which is reasonable, which is practically sort of what we would expect as you increase the number of bedrooms. Okay, so such a bigger house would have a higher price. Okay, but now when we have other variables, which we have seen through the correlations, that they are all positively correlated with each other, bedrooms suddenly has a negative coefficient. Okay, this is one of the sort of effect of having correlated variables being fitted in a model. Okay, right? So the signs sort of flip, and they go in sort of the opposite, intuitively the opposite direction. Okay, right? So, but again, we'll come back to this later on, okay? And we'll worry about exactly what to do when we have the problem of multicollinearity. Okay. Going back to our interpretation. When you have categorical variables, we've already seen what interpretation of those coefficients now stand for, right? For a categorical variable, those coefficients are just the estimates of the group means, right? So in our fitted model, as given at the bottom here, right, the way you interpret the coefficients for the 4 different categories is always going to be in reference to the reference category, right? So beta 2, for example, here represents how much of a change in log price is expected over a house which has condition 1. Right? Okay? It has the same slope as before. Okay? But just because the house is of condition 2 rather than of condition 1, the intercept is now different. It is beta 0 plus beta 2. Okay? Right? and which, visually speaking, essentially produces your models, your linear models, as parallel models or parallel lines. Right? In this case, given that we just have one quantitative predictor, these are lines. If you have more than one, they're going to be planes in higher dimensions, right? Okay, but the idea is that they're all sort of parallel to each other, having different intercepts, right? Finally, when you have a model with interaction, which we've already just discussed, you get models with not just different slopes, not just different intercepts, but different slopes as well. Okay, so going back to that picture, right? When you have a model with interaction, it allows us to not only have a different starting point for the relationship between log price and log square foot living area, but it allows us for that relationship to change at a different pace, right? So when, as we can see, for condition 5, which is sort of the best condition that a house can be in, okay, log price increases with log living area at the fastest rate. Okay, it's got the highest slope. Okay, whereas the one which has the lowest slope is when condition of the house is 2. Okay, and this was sort of seen in our box plots of the 5 conditions. Okay, notice how condition 2 sort of is on the lowest end, right? The relationship that you sort of see here is more like that. Okay, right? So you go condition 5, then 3, then 4, then 1, then 2. And we can see that in our slopes of the different lines. We have 5, then 3, then 4, then 1, and then 2, which has the lowest slope. Okay? Does everybody get that? Right? So that's sort of what the model would look like under having an interaction term, right? So for example, when condition is equal to 2, okay, your model essentially looks like log price, which is beta 0 plus beta 1 log living area, plus beta 2 when condition is equal to 2. The rest will all become 0 except for the beta 6 term. Right, so the orange model is when condition is equal to 2, right? For condition equals 3, we can have this green model, right? So it would be beta 0 plus beta 1 log living area plus beta 3 condition equals 3 plus beta 7, right? Okay, but all of that can be encapsulated in a single parametrization like this. Okay, in particular, when you have categorical variables, okay, for each house or each observation that you have, okay, not all of the beta 2 onwards will have an impact on log price. Okay, right? Because depending on the condition, some of those coefficients will be suppressed. Okay? Does everybody get that? Right? So that's it for today. We're going to end our lecture a little early today because for diagnostics, we'd like to start off fresh. So tomorrow, when we meet, we'll start with model diagnostics. Okay? So again, just a quick reminder, model diagnostics is all about checking for our model assumptions, right? So all about checking for constant variance, making sure that our errors are normally distributed, making sure that the linearity assumption is met, and so on and so forth. And then finally looking for outliers and influential points, okay? All of this becomes a little more complicated now because we are in a multiple regression setting where we have more than one predictor variables. Okay, but we'll talk about all of that in more details tomorrow and next week. So thank you. See you all tomorrow.